first. Yep. Alright, another day. Welcome back, everyone. So, if people want to submit problem requests, those should be open now. There's also something special I was supposed to do. I forget exactly what. Oh, yeah, I wanted to make a blurb about the n-1 equal value principle. And yeah. It might be a slow day today because the kids from the United States recently had they had their short answer contest today, the first round of the US math competition series. So a lot of them might be feeling pretty tired. We'll see. What does the V stand for in your Twitch handle at VEnhance? The entire thing is an anagram. Those are all 8 letters. Hi, Leo. Hard short word. Oh, that could be a while. I am not good at algebraic geometry at all. Let's do AMC 12B problem 24. Well, presumably you have enough channel points to request that. Okay. Alright, first problem request. What is this 20? Oh. Is this 24 going to be a meme or something? I feel like every AMC there's a few problems that stand out for whatever reason. Either they're terribly misplaced or like they're unusually brutal, and I haven't looked at the test at all other than the fact I know apparently I have one problem on the AMC. And that's like about it. Okay, so it might take a while for people. I'm getting the feeling that it's like a kind of a slow day and people are still trickling in. So I will, I promised that I was going to do a blurb on n-1 equal value principle and a blurb on Hensel's lemma. So I'm going to do both of those now while waiting for, well, or I can do n-1 EV now and save Hensel for next week. Oh, decisions. Okay, actually, you know, let's let the chat decide. Elmo 2010 3. Okay, that's... Yeah, I guess no one cares about inequalities. Okay, that's fine. I'll do both. So let me get the whiteboard set up. Can you motivate me to learn homology? That's an interesting request. Okay, we'll start with Hensel's lemma. Man, at some point I really should like simplify the setup a little, because it's actually getting to be a bit much. Like there's so many moving parts that I'm having a hard time keeping track of them. Problems been chosen? Iranian geometry. Problems have not been chosen. I am doing a couple short videos that I've been promising that I'm going to do. How does polling on Twitch work? Yeah, I have a separate overlay for that. The site I use is poll.ma.pe. There's also a native Twitch. Twitch has a native poll system, but I like the other one better. The native one stopped working for me at some point. Probably because I'm on Arch Linux and things just break on Arch Linux. Okay, cool. Okay, hi everybody. This is going to be a short video where I'm going to quickly explain what Hensel's lemma is for math competition purposes and like, yeah, okay. That's all I had. So Hensel's lemma, this will work a little better if I have some motivation. So let me start with a particular example. Let's say I have the polynomial f of x is oh crap, did I close the window with my notes? Okay, you know, this is already a disaster. Okay, let me just start over. Okay, hi everyone. This is going to be a quick video where I will give a bit of an example that demonstrates what Hensel's lemma is supposed to look like, and then I will give the statement of Hensel's lemma. This is for Olympiad purposes, so it's focused specifically on numbers modulo p, and I'm not going to give the statement in the full generality for like a generic number field or with like a place or whatever. So, let me start with the following. We're going to look at the polynomial f of x equals x cubed plus 17. And we're going to be interested in this polynomial modulo 5. So f of x looks like this, and modulo 5, the polynomial f has a root at x equals 2. So what I'm going to do now is I'm going to look at what the value of f is modulo 25 at this root. So when I look at modulo 25, this x equals 2 root sort of lifts into 5 different roots. You're interested in f of 2, f of 7, f of 12, f of 17, and f of 22. This is quite zoomed in. I don't need to be that far zoomed in. Okay, so let's compute what happens when I look at this mod 25. So this number is going to be equal to 0, mod 25. And then the number after it, 7 cubed, is 343, plus 17 is 360, so this is 10 mod 25. Then if I look at 12, 12 cubed is 1728, plus 17 is 1745, which is 20 mod 25. I already have a typo, apparently a misspelled polynomial, so let me fix that. And f of 17, 17 cubed is, 4,913, I hope. Plus 17, take mod 25, I get 5. And 22, I'm not even sure I can do. Let's see, 44, 968, 10, 648, 10, 665, 15. So I already knew all these numbers were going to be divisible by 5 because like 2 is a root mod 5. So when I plug in numbers that are 2 mod 5, I will always get things divisible by 5. But when I look at these numbers, they have this very nice property where they are actually an arithmetic progression. It's like 0, 10, 25, 15. And in particular, what this means is that I get every root, or every multiple of 5, exactly once. Like 0, 5, 10, 15, 25. Or, sorry, 0, 5, 10, 15, 20. Modulo 25. So this is what I'll call like good behavior. What happens is that I get each of the possible residues, modulo 25, that's divisible by 5, exactly once. And in fact, they're always an arithmetic progression. So why is that happening? Well, we can dig a little into it. What's going on? Well, let's just say, in general, if f of x plus p minus f of x. I'll evaluate it for this specific polynomial, but the same calculation will just hold in general. The 17s cancel out, and I will get something like 3x squared times p plus 3x times p squared plus p cubed. And if I only care about things modulo p squared, this stuff all goes away. So I only care about the terms that have a single p here. And this is some number. And this number is always a certain thing. Well, for our special case for x is always 2 mod 5, this will always be 12 mod 5. And more generally, what will always happen is f of x plus p, and so on. This thing, this is always an arithmetic progression modulo p squared. So if x is a root, then f of x plus p, f of x plus 2p, and so on, because of this calculation, you get like p times the thing that has a fixed value modulo p. So yeah, always AP. And so now you might be like, oh, this is really great. This might mean that, the theorem that we hope is true is that if f has a root modulo p, then because of the arithmetic progression, we might think that this means then f achieves every multiple of p modulo p squared. That would be like what's the, in an ideal world, this might be true. Unfortunately, this is not true. And to give a counterexample, I'm going to look at the polynomial g of x equals x cubed plus 3x plus 17. So this polynomial is a little different. And what happens is when I compute g at, so g still has a root at, sorry, let me not use 17. I wanted to have a root at 2. So x cubed plus 3x plus 1 when I compute this, this is 15. G of 7 is 15 mod 25. G of 12 is 15 mod 25, and so on. So they're actually all 15. So it is still an arithmetic progression. However, I mean, it's an arithmetic progression with common difference 0. So the theorem does not hold for this case. So the upshot of this is that if I have a root mod p, then when I look at it modulo p squared, it will always be an arithmetic progression, but it could be the case that the common difference is 0, which is sad. You know, this is a little bad. We would want it to hit every number exactly once, but here it's stabilized at a certain number over and over. So the question is, I'll get to higher powers in a moment. So the question is, how can I tell these apart? Like, how do I know whether I'm in a case where the common difference is non-zero versus when the common difference is 0? And the answer is that if you look at this quantity, it's a really big hint. This quantity might look like a quantity that you're very familiar with, and it turns out that this is essentially, if you do the calculation, you will find that this green bit is actually f prime. It is the derivative of f. You can check this for polynomials f. So the way to complete the statement is to say, if f has a root r modulo p, then f achieves every multiple modulo p squared under the additional condition that the derivative is not equal to 0 modulo p. So this is the condition that makes that common difference non-zero, because it turns out the common difference is exactly given by p times this number. Okay, so that is that. So someone was asking in the chat about, well, what about higher powers? And it turns out you can do the exact same calculation where if I take this 2, I can replace it with k for any k at least 2. And what happens is if I know that it's equally distributed mod p squared, then instead of f of x plus p, I look at f of x plus p squared and repeat the proof, and it'll do the exact same thing. So this result is called Hensel's lemma. It is basically telling you that if you have a root modulo p, then by looking at the derivative, you can tell how that root behaves when I look modulo p squared, p cubed, p to the 4, etc., etc. Okay, and that concludes the statement of Hensel's lemma. For Olympiad purposes. Again, when you look on Wikipedia, you'll find a version that is stated much more generally for algebraic number theory, but this is the statement here. Okay, I should duck slightly out of the way so that I'm not covering the statement. Good reason to slouch a bit more. So that concludes this short Evan Explains video. Thanks for tuning in. Yeah. Okay, cool. Camera off. So for context, the reason I'm doing these videos is because I have to give this explanation like once a month, and I'm kind of tired of it, so I want to record it once and not have to do it again. Okay, so the other thing I was supposed to explain was the n-1 equal value principle. Hensel's problem suggestions. Let me see. UCMO 2019 problem 2 is good, I think. UCMO 2020 problem 6 possibly fits. Yeah. Hensel's is not actually a very hard statement, I think. Like, it's one of the things that you could probably discover yourself, but because it has a name, people are scared of it. Like, I think Hensel's is one of the cases where giving that particular lemma a name has made it more scary. How do you suggest a problem for you to solve on stream? So under rewards, so underneath where it says send a message, there's a place where you can spend V-Bucks to request problems And yeah, you can use that. I think I should decrease the cost, honestly. Because at this point I get so many requests that the cost doesn't matter and I should be a little more egalitarian. Let me do that. Edit rewards. Customize points. Manage rewards and challenges. Okay. $512. Okay, prices have changed. Yeah, so my understanding is that a problem request is worth like watching the stream for a couple hours, which I think is reasonable. It's sort of like, that's about watching like a day so you have a sense of how the stream works, and then after that you can request once a stream. Wait, how do I hide? I'm not sure there are spoiler tags in Twitch chat. Yeah. Okay, so I was supposed to explain n-1 equal value principle. Binge watching all the YouTube content. Ah, okay. Yeah, I can forget that most of my viewers are actually on YouTube and not on Twitch. Yeah. I also know a lot of my students will like just open the stream and then leave it open just to farm the points, which I find hilarious. And yep. Oh well. Actually, I should move to the right so that the okay, so okay, I'm so glad that I'm finally doing this because I've given this presentation at least 5 times and it's just like, I should just do it once. Alright, lights, camera. Okay. Hello everyone, so in this short video I'm going to be explaining what's called the n-1 equal value principle. And it goes as follows. So let's suppose you have some function, you have some known function f from R to R. And you have a fixed integer n. Fixed integer n at least one. Well, let's say n at least 2 actually, so it's not vacuous. And you want to min or max. Let's say minimize. You want to minimize the value of f of x1 plus f of x2 plus plus f of xn subject to x1 plus x2 plus blah 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 plus xn is equal to 0. Or any other constant. This constant doesn't matter actually. So let's just say constant. So when you do this, when you have a problem of this shape, there are sort of 2 things that you can always mechanically check to see if they will work. One of them is, say, you should check whether or not this function f is convex, because if it's convex, then you use Jensen's inequality, and it will insta-kill the problem. Because Jensen's inequality tells you that this sum, which let's call this sum capital S, it will tell you that this sum is at least n times f of the average, and you're good to go. If the problem doesn't die immediately to Jensen, then what you often might check is, does f, you do something that's called the tangent line trick, which you can search on my website if you want. It's a trick where you take the point where you think there's an equality case, you draw a tangent line and see if the curve lies above the tangent line. And if so, that will usually solve the problem. N-1 equal value principle is a tool that you can use if both of these two earlier methods fail. It is a lot uglier in most cases, but it can work, so hence this video. So how does this principle work? This principle makes one assumption about the function f. It assumes that f has exactly one inflection point. So if f has exactly one inflection point, then let's say the picture looks like this. So here's the inflection point. And then you have like the concave part here. And then you have the convex part here. So So that's what our picture looks like. Okay, so now let's suppose that we have some points. So here's like, let's say our picture looks like this. It's x1 here, x2 here, x3 here, I don't know, x4 here, and then like x5 here or something. So here are my 5 numbers, and I want to try to decrease the value of s. This quantity is over here. Well, how can I do that? Well, I can do a thing where if I know where the points initially are, I can try to move them in such a way that s decreases. For example, if I look at this point here, at this x4 and this x5, thanks to VT for the chair, these 2 points lie in this convex part of the function. So what I could do is I could try to push them closer together. And Jensen's inequality tells me that in a convex part, if I push 2 points closer together, then that will decrease the sum. So I could improve the value I have by getting rid of this point, getting rid of this point, and instead making x4 and x5 equal to each other at the midpoint of those 2 things. So this is an example of a move that would improve my value of s. Yes, assuming that those 2 points are on the convex part. So this is just an example with this picture. Like in this picture, if I have 2 points on the convex part, I can push them closer together, and that will improve the value of s. Okay, so that's fine. Let me undo this now, just to rewind the picture back to its original state. Yeah. Okay, so now the slightly more confusing part is that there is a concave part here. And for a concave function, the opposite thing is true. If I want to decrease the value of s, and I have 2 points, the way to do that is to push them farther apart. So for example, I could take this x1 and this x3, and push this guy to the right, and push this guy to the left. So maybe this x3 ends up right here, and this x1 ends up here instead. That's not x cubed, this should be x sub 3. So this is an operation that will also improve my value of s. So to summarize, in the convex part, I want to be pushing the points closer together. In the concave part, I want to pull the points further apart. So the idea behind the n-1 equal value principle is that, well, I want to keep doing these types of operations until I can't do them anymore. And my goal is to get as many of them equal as possible. So my strategy is as follows. I'm going to first, in step 1, take x1, the one that's farthest to the left, and push it very far to the as far to the left as I can go, while pushing this guy, x3, this guy, x2, all the way to the dividing, like the edge of the concave part. So x1 will be somewhere very, very far to the left, and x2, x3 get moved so that they are at the midline. So I'll update my picture now to reflect that. So after the operation, I end up with x1 here, and x2, x3, I'll draw a big point because there's 2 of them, x4, x5, which are all in the convex part. And now, okay, well, the convex part I want to push them closer together. So I take all 4 of these points and push them to wherever the average of the 4 points is. So you get some giant point here. Let's do that. So you push them. So these points all go away. Bye bye, bye bye. Oops. Don't want to kill the curve. No. Yeah, there we are. There. And now here is x2 equals x3 equals x4 equals x5. So the upshot of this argument is that if I had like at least 2 points in the concave region and at least, well, any number of points in the convex region, then I can improve the value of s by pushing x1 all the way to the left and pushing everyone else so that they are like at some equal point. So let's then sort out the edge cases. If there is only 1 point in the concave region, that's fine. That means everyone else is in the convex region and I squeeze them together. If there's no points at all in the concave region, that's even better. I just use Hensel, push this all together. So the resulting theorem statement is that in this situation, optimal values of f, of s occur when n-1 of the variables are equal. That's what the theorem says in this situation. Okay, so someone's very sharp and is asking, does it work on an interval? Because, well, some of the points might fall off. And the answer, first of all, why should you care? The reason you should care is that because most of the time when you do an inequality on math competitions, very often the real numbers are actually constrained to be like non-negative or something like that. Yeah, I am an affiliate. Yeah, not a partner. So what that means is sometimes, let's say you have a condition where your variables are constrained to be non-negative or something like that. That's not supposed to happen. Then this argument will break because you are, in this argument, you might end up pushing the red point past the non-negative barrier. And the answer is that it depends, because your function might be concave to the left and convex to the right, or vice versa. So the answer is that you have to draw the specific situation for your problem and think about it. In this situation, it's not okay because the argument will push points far to the left. However, if I was working on a problem that was flipped around, where I'm trying to maximize the value of s, then the argument is okay, because the argument will never push a point to the left of my inflection point. Or if I had a function which, instead of being concave on the left part and convex on the right, was instead the other way, where it's like convex to the left and concave to the right. If it was flipped so it looked like this, then it will also be okay, because the convex part you push them closer together, on the concave part you push them farther apart, and your constraint non-negative is at the left. So intuitively there's like there's sort of like 4 possible things that can happen depending on which half of the function is convex versus concave, and whether you're trying to maximize or minimize s. And if you have a non-negative real condition, it will work basically half the time. Could this be used with multiple inflection points? I think with multiple inflection points, you can use something like it. I mean, you can work through the argument, right? The point is that this argument is very concrete. You can draw a picture and say, because I want to maximize / minimize s, I push here, pull there, and you can follow through the argument and see what happens. Depending on what setting you're in, it may or may not work. So this theorem here is only stated for the simplest situation with exactly 1 inflection point and no conditions. And most of the time, you will have to work out your specific case because there's probably some extra condition, and see what happens when you do so. But that is the n-1 equal value principle. It is a way that you can simplify your inequality so that a lot of the variables are equal to each other. Okay, so that concludes this video. So thanks for tuning in. Hope that was informative, and I hope that I don't have to use this anytime soon, because let me tell you, even when it does work, like setting n-1 values equal and then like using calculus on the resulting thing is not especially fun. But it's here if you ever need it. That concludes this talk. Okay. Evan, how would you approach a difficult problem during a timed event or in general? That's a very broad question. So I would say I actually said this last Wednesday at a talk I was giving, where I said one of the things that I had to respect about hard problems is you need to start doing things where you have to do things that will help you understand the problem better, even though they won't solve it. Like up until like USUMO 1-4-ish level, you can often get away with only trying things you think will solve the problem. And past that point, that sort of stops working. You need to be able to... The stereotypical example is small cases. It's like you work on this problem that's stated for general n, but you specify to a case where n is prime, and work with that case, and then even though that case won't end up in your write-up, it will still like, it's still, the point of doing that is not to solve the problem directly. It is to inform you about which things to try that might solve the problem. And being able to do things like this is the key. I always hesitate to give small cases because small cases is sort of the dumbest one, and the one that people don't understand necessarily very well. Like the way that n small cases is done is like, oh, you do n equals 1, 2, 3, 4, and then hope that the answer is a guessable function in n. And I think that is really underselling the I think that's really underselling it. But it's the most accessible example. But other things like giving a heuristic argument that a statement should be true or not true, for example, is a skill that you need to start being able to pick up when you're doing harder problems. Even though you can't prove a statement is true, you should be able to tell whether or not it's true, and that will often guide you. A lot of this sort of meta thinking, I would say. Yeah, equality is the... If you do Otis, the equality unit is the point where I really hammer this into you. It's just like... Yeah, heuristics are very important. I'll put it that way. Cool. Okay, cool. So it sounds like we have problem submissions. How many? International Geo Olympiad. Okay, let me fish these all out. I might have done Elmo 2010-3 before. It sounds familiar. Never mind, I haven't. Okay. Give me tag Elmo. Have I not done this? Really? I look at the statement for Elmo 2010-3. It looks super familiar, but I don't think I've... okay, I guess I haven't done it because I don't have a record for it. But I'm surprised. So the only thing I know about the AMC is apparently I have one problem on the AMC 10 that I think should have been, well, I submitted it for the AMI originally, and I guess it eventually made its way to AMC 10, so that happened. Yeah, otherwise I basically don't know anything about the AMC. But someone suggested an AMC problem, so I guess I'm about to find out. Oh god, the animal problem is so long. Alright. Oh, no requests. Okay, alright. Man, I really can't keep up anymore these days. AMC 12B number 24. Okay, I'm gonna assume 12B was a typo for 12A because I don't have the 12B problems for obvious reasons. And someone already requested it, so good job. You got your... Wait. 3 people requested. What? Okay, I'm gonna randomly pick one person. To... Or I can charge everyone for it. No, I'll randomly pick one. Okay. Well, we'll charge the last person who submitted the request. I don't know. Okay, I gotta do something, right? I figure you guys are happier if I charge only one person for the request. Alright, so... Okay, so what is this AMC 12 problem that people are... Yeah, what is this AMC problem that everyone is clamoring about? That it got submitted 3 times. Do I want to see it? Oh my god, how do you search for problems? Oh jeez. Plus 12A, plus 24. I hope? Okay, found it. Oh god, it's Geo. 10A number 17. You realize that... Okay. No, you know, because I told you already. We're not doing the 17. Okay, I'm gonna delete the answer extraction, because it's annoying. Okay, this is AMC 12A number 24. Okay, what else? So... Okay, there's a British MO problem that got submitted. I'll take that one. Oh, that problem looks really cute, actually. Really? That's true? Wow. Okay, so then I'm looking for CIAM 2019. Which one is problem 4? I don't... That's 2. I can't find the CIM problem. Where is it? Okay, I'm gonna go grab a different problem first. Can someone send me the statement of the CIM at some point? So I can't find it. Also, for whoever requested the Iranian Geometry Olympiad, should I be looking at the advanced problem? Like, it looks like there's levels. I'm gonna assume it's advanced. Let me know if not. Oh wait, oh, the request is over problem 3. Oh, freaking, oh. Let's try that again then. I also can't find problem 3. I found 1, 2, 5, and 6. I haven't found 3 or 4. Okay. Yeah, I don't know which one is. Okay, in the meantime, can you check your whispers? Which button do I press for that? Oh, that one. Okay. All right, so let's do the vote. Which problem? Yeah, I don't think. I think I think I know what's about to happen though. Yeah. Hey. Yeah, problem. The British problem actually looks super cool. I think I'm definitely going to do. I hope to get to that one today as well because that is a really sweet result. Holy shoot. Like I'm astonished the result is true. Like looking at this statement, I'm like, seriously? It's BMS prepare. Oh, I don't care what the proof looks like. I think the result's still cool no matter what. No, I haven't saw. It's just I think the result, like the statement, looks very surprising. Like I'm really surprised the statement is true. I know I have a bit of an idea why it's true because there's a USMO 2007 problem that says that the AIs are eventually something. No, actually that's a different result. Yeah. I assume it probably shouldn't be hard given that it's true. I'm just like very impressed that it's true. Okay, well, that landslide. All right, let's get started. Okay. I am skeptical I'm going to solve the problem given that everyone wanted me to do it. Okay. Let's use the board, alright? Yeah. I have failed to solve an AMC 12 number 12 on stream before. By which I mean someone very heavy-handedly told me what I was supposed to do, and I was like, oh, okay. Okay, let's get started. Alright, everyone, welcome back. So for today's stream, I have problem 24 from an AMC 12, which is being proposed for Twitch Solves IMO shortlist. So the definition of IMO shortlist, I guess, is becoming increasingly generous. I hope I am able to do it. We'll find out. So there's a semicircle AB with diameter 14. Then there's a circle tangent some point P, and there's 2 points Q and R. And we're told that QPR is 60 degrees. Let me do the 60 degrees in different colors. This is all the same color. So we're told that this thing is 60 degrees and this thing is 3 root 3. And I want to find the area of triangle PQR. Okay. Okay, sure. Okay, let's see. So radius 7, fine. So I'm going to just start by adding the centers for lack of anything better to do. I'm told that this angle... I feel like that angle... P feels like it doesn't... Oh, no. I need to also use the fact that it's tangent. Okay, sorry. Let me actually think this through. Well, okay, I'll draw this either way. Here's the center, O. We don't really need that 14. And... okay, and we'll call this S or something. So this is a 60... This is also 60 degrees because it's the... Okay, sure. So we have a bit of control of what's going on. So we know... This will tell us what the radius of that circle omega is. Because it's equal exactly to this. So this length here is 3/2 root 3. So the radius of omega is given exactly by help, how do you do trig? 3? Is it just 3? It's 3, right? Yeah, so this length here is like 3/2. And so this is 3. Okay. Now what do I do? So at this point, I'm wondering how much of this picture I should be deleting. What do I need to get the area of ABC? It's like... Okay, so what I'm going to do is I'm going to... I just had a thought, which is I'm going to construct the bottom half of this circle. And the reason is, so I had the thought in my head that there's a formula for the area of a triangle that's called ABC over 4R. This is the area. So because QR is known and also the radius of PQR is now known, it's sufficient to compute PQ times PR. And PQ times PR I can get if I... Oh no, sorry, this doesn't work. Never mind. I was about to like draw this thing or something, but I don't think that's correct. Nope, belay that. But basically I need PQ times PR. Actually, I need that anyways because I want the area, and it's the 60-degree angle included. Oh, okay. So I feel like... So this is 7, right? These are all 7. So it's like I don't know what the distance between the centers is. And that is going to be kind of pinpoint. But by power, okay, so by power of a point, okay, I can actually get that distance, because by power of a point, no, I can't. No, that's just Pythagorean theorem. Oh shoot. How do I compute OS? Do I know OP? Isn't it just 3R? Okay, I'm sorry, I'm missing something obvious. Pythag with QR. Oh, sorry, yes, okay, of course. So OS is given by... Let me delete this and use the second half. So this means I need to draw the point M here. So OM is given by square root of 7 squared minus 27 quarters, I guess. That's 3 to 3 squared. And then minus this little guy here, which is given exactly by 3 halves. So let's hope the numbers are nice. They are. So this is equal to 13 halves minus 3 halves is equal to 5. Thank you, bench, for the follow. So this is 5 and this is 4, I guess. That seems useful. Okay. Okay, so actually this diagram is now basically determined, right? Like if I was trying to construct the diagram, I start from that 3, 4, 5 triangle. And... yeah. However, this is not... Okay, so is there a good way for me to get, like, PQ times PR? And compute the distance from P to QR. Oh, I guess that works. Yeah, I guess that will work. I'm a little reluctant to do it, but I don't, yeah, that's fine. We can do that. So let's do this. So this is 3. And so we know there's a similarity to a... So this triangle here, how do I highlight it? Here. This is a 3, 4, 5 triangle. So this giant triangle, which has sides like 5 plus... Oh, jeez, hang on. Which length is... That 3 halves is labeling this thing, right? This thing? Okay, so this is like... Oh, jeez. Oh, this is annoying. Ah! Okay, so this is 5/3. This whole thing is 5/3 times 5 plus 3 halves, which is 13 halves. So that's 65 over 6 minus 7. So this is 23 over 6. I hope. So that means this thing is 41 over 6. Okay, great. And for it, did I miscompute? 65. It's not like out of 8. Oh, did I fucking screw up? Oh yeah, I screwed up. It screwed up. I used the wrong denominator. Okay, sorry. This is a 5/4, not 5/3. Okay, so this is 65 over 8. So that means this thing is 7. This is 9/8. And then plus 3 is 33/8. Okay, so that means the altitude from P to against the... Jeez, this is very... Okay, so the height from P will be equal to the height from O times an aspect ratio, which is like 33/65. The height from O, we agreed, was 13 halves. So this is 33 over 10. And finally, the answer is 3 halves root 3 times 33 over 10 times 1/2, if I didn't mess anything up. And that is 99 root 3 over 40. Oh, sorry. No extra 1/2. Yeah, that's already halved. So 99 root 3 over 20. I hope. So, so I'm supposed to bubble in the answer choice that is 122. Yeah, this feels like an AMCGO. This does not feel like an AMCGO. Oh, actually, I think the tail end of the AMC has gotten really hard over the years. I agree, it's like an AMCGO. It would be a good AMCGO problem, I agree. Stumbling. AMC 12 used to have harder final fives. I don't know. Yeah. Oh, it looks like I have, so I think I have like basically the same solution as kind of. Yeah, that's like exactly the same. Oh, the point needs are also almost exactly the same, except we used O for. What's in social lounge? I will not make Evans suffer through it. Wait, what? I'm confused. Anyways, let's go on. So I'm doing the British problem next, right? Okay. 2017 G 1, 2, 3, 4. What were they? G2. I.e. the one that was actually on IMO. Okay. Alright, welcome back everyone. So today we have a problem from the British Olympiad in 2021, where you're given a sequence of integers a1, and each n is the smallest thing that is different from the previous ones, and such that the mean is still an integer. So let's give this. So why don't we start by like picking a random integer and giving this a spin, seeing what happens. So I'm going to start with like a1 equals 9, just as a random choice. So if a1 1 equals 9, then the sequence goes a2 equals 1. Contains every integer exactly once. So I guess this is going to include negative integers, which is fine. So a3 will be 2, I guess. So that makes the total 12. You know, this actually works is better on a board, because I actually want to make a table. So let's change gears. So a1, if we start at 9, then the mean is 9. And then a2 will be 1 for a mean of 5, 2 for a mean of 4, then 4 for Do I want the running? Let's just make the whole table 10, 12, 16. So sigma, mean. I also keep track of AI minus I. So did I mess up already? Wait, what did I do wrong? Yeah, you're right that this gives -1 twice. Oh, sorry, I don't think you get to pick A1. Okay, yeah, sorry. This is actually a single sequence. It's not a family of sequences. I think A1 has to be... I misunderstood the problem. So there's only one sequence to study, which actually makes my life easier. Yeah, okay. Okay. Should I just start the YouTube intro over? Yeah, let's just restart the video. Okay. Welcome back, everyone. So today we have a problem from the British 2021 problem where you start with you have the sequence as defined the following way. So it's the smallest positive integer for which the arithmetic mean is given by the arithmetic mean of the first n terms as an integer, and also yeah, they're different from all previous terms. So a1 is by definition equal to 1. This is a mean of 1. So this ai minus I is 0. For a sub 2, we need an odd number. So this is really 3. And so this mean is 2. Sorry, I'm already mingling the columns. Well, we'll make this column an. 1, 3, 1, 4. A3 is equal to something. So I want to be divisible by 3. So let's just figure out what the sequence is first. 6. This makes the mean 2. Okay, now I want it to be divisible by 4. 2 is taken, so 6 is the next thing. This is 12, mean 3. A5 will be given by 3 is taken, so I need 8. Two, 6, 8. And now I want to be divisible by 6, so this is 4. 24, 6. A7 is... Okay, so 4 is taken. So at this point, I want to start keeping track of like when I'm saying number is taken, because yeah, like here, this is a situation where 1 was taken, so I took 3. This was a situation where 4 was taken. Yes, like some of the numbers are bigger than indices and some of them are smaller. I want to start tracking that information because it feels possibly relevant. 11, 35 for an arithmetic mean of 5. No. Oh, this mean should be 4. Okay, so let me keep computing a few terms. So 8 should be 5. That is not, in fact, not taken. So 5, 40 means these are 5. But for A9, the number 5 is... So I'm noticing this thing where like this 2 is this 2. I think these might be the same. Like, I feel like I might be in one of two cases. Like either you increase the previous... Did I mess something up? Something about this feels a little off to me. So Okay, the previous number is always the arithmetic mean or the arithmetic mean plus the index, I think. Like it's either 2, plus 7. Plus 2. Yeah, I haven't seen an example yet where it skips by 2, and I'm inclined to believe it probably doesn't exist. But let's keep going, so we have more data. Because this is a problem that only involves like a single sequence of numbers, I'm very happy to mine it for a lot of data, because it's not like I have to do this for many examples. This is the sequence, so to speak. So this number is not 5. I want 14 here. And 14 will give me an arith 54 for an AM of 6. And a 10. So how do I... which numbers are appearing? So 6 hasn't been... No, 6 has been used already. So... should be 60 next. 7. And 7 has not been used. 1, 2... So this 7 will appear. Okay. So red, green, red, red, green, red, green, red, red. Okay, so now I'll at least pay a little attention to the extraction. So we're being told that every integer appears exactly once in AI minus I. Let's see what that looks like. 1, 0, 1, minus 1, minus 2, minus 3, 2, hang on, minus 4, minus 3, minus 5. Okay, so it looks like the extracted integers are... oh, did I... sorry, I am subtracting the wrong things. Let's try that again. 2, 6 minus 4 is 2, 8 minus 5 is 3, 4 minus 6 is minus 2, 11 minus 7 is plus 4, 5 minus 8 is minus 3, 14 minus 9 is 10 is 6. Well, okay, we actually, we think that the... Yeah, actually, hang on. This might not... This might just be the same thing we've already been doing. I'm trying to see if I can tell when it's going to be red versus green. 1, 3, 4, 6. When is it red versus green? So right now what we know is that each AI is either the... We think that each AI is either the arithmetic mean or... I mean, we know each AI is congruent to the arithmetic mean modulo the index. And the smallest thing that can happen is it's equal to the just arithmetic mean period, or it can be increased by plus I, in which case the arithmetic mean will increase by +1. So basically I can compress all this data into just like when does the sequence when does the mean like increase or versus stand still. And I don't know. This one is arguably green. So, like, I don't even... Okay. Green, red, green, red, red. Green, red, green, red, red. Green... Maybe it'll be periodic mod 5. That's a long shot. Let me see. I want to make sure it's not just periodic. Okay, who gave me... Someone gave me terms. 5, 14, 16, 7, 19, 21, 9, 24, 10. So if I had computed the next terms, it would have been red, green, red, red, green, red. So, okay. Green, red, green, red, red, green, red, green, red, red, green, red, red. Okay, so it's not just periodic. Yeah, that was a long shot. Okay, so, alright, I'll pay a little more attention to the integer extraction following Eknerwal's suggestion. X always appears before negative 6, yeah. So, yeah, what happens if I just completely substitute out AI minus I for I? So... Let's see. Okay, wait. No, we're finding more patterns. X appears X terms before minus X? Wait, that's really strong. Oh, that's neat. That's actually... Wow, that's really strong. Also, what the heck? Really? No, I think that pattern is right. 5 goes to... Huh. I think that conjecture is right. And if so, that gives us I don't know what Wythoff's scheme is, honestly. But the opponent to the solution is way simpler. Alright. Okay. I know Wallace says we're getting nerd sniped like heck. So what am I missing? Let's write the condition in terms of AI minus I. Alright. I've done geometry problems that are like that, where we just spent the whole time like chasing a lot of things and it turned out like none of them were relevant somehow. Which for Geo is like really sad when that happens. But yeah. There's a problem where we would have solved this problem faster if we used Microsoft Paint. Okay, so we're just gonna look at BI equals AI minus I. Yeah, no, it's fair game if you haven't seen the problem before. This is the stream is called Twitch Solves Isl because I actually can't do all the problems myself. So I look at BI and the condition I want is that. How do I do the distinct condition? So BI plus I should not equal BJO. Oh no. This one looks familiar. For all. So initially it starts here. And also there's a mod condition. What's the mod condition? It's the I divides 1 plus things plus I plus B1 plus BI. Like that? Yeah, we should. I want to go. Yeah, we should go chase that for that pattern because that pattern's cool. Right, where was I? So. So this is B1. This is a picture that corresponds to B1. What am I missing? BI plus I. The diversity condition is kind of shitty. Although, okay, like we know that it's either we think that the BI, ignoring that divisibility issue, we think it's probably either yeah, let me not think about this divisibility too much. So B1 is 0, so it's like here, and it emits an arrow like that. This is B1. And this is plus 1, so it emits an arrow like that. Why is B2 plus 1 and not minus 1? Because, okay. And then B3 is... Wait, I think this is just an explicit description. I feel like I'm looking at the BIs and like... Okay, let me think this through. And it gets filled in. I don't see I don't see what the simpler solution is that I'm not seeing. B2, B3. Look at the set B1 through B2 to BK. 0, 1, minus 1, 2, 3, minus 2. Oh, are you serious? Okay, I know what's going on now. I should have recognized this. This is totally my fault because this argument has showed up before. Is your pattern true? I bet it's true. I am convinced that it must be true. And how does kill the problem? Okay, so the claim is that the set of BIs, like the set of numbers BI is always a consecutive set. So, you know, it starts 0, 1, 0, and minus 1, say like up to... And the proof is by induction. The reason is that if it's true up to here, then the next number, the congruence relation tells you that BI should be congruent to either -2 or 4 mod 6. BI is non-negative, so the clash condition or BI is at least negative I. So -2 and 4 are both candidates, and one of them necessarily works. Because if -2 doesn't work, then 4 definitely works. Because then the 4 plus whatever will be bigger than the any of the other things. So if -2 happens to not work because there's a smaller index height that generates collision, then the +4 will work. So that means you now get this one as well, and then it continues by induction. If you've seen the IMO 2005 problem, which is the reason I pulled it up, it's the same type of induction. It's just at every point I claim that they're a consecutive set, and then there's two numbers that you can add that are plausible. If the negative number fails, the positive number works. So proof completed by induction. Oh man. C++. Yeah, strictly speaking, I need to show that it doesn't. Okay, that's true. Yeah, I need to show it gets both infinitely big and infinitely small. But yeah, that's presumably straightforward. Wow. Okay, so why is this pattern true though? This is definitely a thing, and I want to know why. Why does it show up exactly? I mean, to be fair, I think the consecutive thing is going to help us a lot as well. So what I need to show is that, first of all, let's see. So if I'm at a point where if I have a bunch of consecutive integers, and here is like, let's say we're at, let's do this in a different color. Okay, so let's say we're at this point. I want to show at this here that I can pick if this is Bn. Oh, okay, hang on. Yeah. B sub I. This is some B sub I or whatever. And this is B. Oh god, the indices are nested. That's not great. Oh jeez. Oh, this is really involved actually. Oh no. Alright, so let me think this through. So when B2, this B2 is equal to plus, okay, whatever. So I'm gonna put two red empty dots here. And when I look at B3, yeah, the fact that they're consecutive is pretty important, I think. It's like, maybe the claim is that not only are the closed dots that I'm drawing consecutive, but the open dots are not the open. What am I doing? I disapprove the signs from Fibonacci word. Orthoff game, huh? Thank you, Sumit Kumarat, for the follow. 3. Minus 1, 2. Yeah, okay. I think I have a vague idea what's going on. Let me see if I can formalize this. So let me keep just those numbers in the background. So I think I can give a visual description of the process. The point is that we know that the BIs are always consecutive. Maybe I shouldn't have erased all that actually. So I think the process can be described as follows. Starting from 0, we draw one arc. So that point is now blue, it's used up. And at each step, the process I think always goes, you fill in this arc. So now it's used up, and this will have a length 2 arc, which I'll mark with 2 dots. And then when there is a pending arc, you can, so this is minus 1, this is B3. It draws another arc here. Lands here. So I think these open red dots go backwards until it meets the blue dots, at which point all of them get filled. So now this gets filled, and it's, this is the 4th one, so I should go 4 points out. Then this one gets filled. So I should go 5 points out. Or something like that. This is really hard to do without. 4, 1, 2, 3, 4, 5. Okay, and then no, what? Hang on. So I'm just confused. Well, okay, I think this is basically a description though. Because at each point, the length of the arrow is actually given exactly by the number of points. So now here I would put in minus 2, and it would go to here. Leave a... Okay, and then put a blue number. Yeah, when I... Okay, so then this is like... Jesus. Like that. And now there's a green dot at the end, so I put minus 3. So I have a way of sort of describing the automaton. And then fill in the red dot, make more things appear to the left. So, because of this, I think this will I'm hoping this implies the pattern that Carther conjectured, where after a certain positive number is inputted, that's how long it takes until the corresponding negative number is in. No, actually, that's more involved. Okay, I actually have no idea what's going on. I'm just making stuff up at this point. This red arrow should go here. It's a fixed point of the transformation. I see. Oh. Oh, frick, I forgot your username here is only just K. Yeah. It's O. Yeah, if it's O of E to the N, I'm not sure you can get more than 38,000. There's a big there's a big difference between O of E to the N and O of N. All right. Okay. Okay, maybe I'll close off the problem here. Okay, so I can either... Yeah, maybe I'll just leave it here. I'm not sure it's that useful for me to keep trying to do this live. Do I want to do more math? What do people think? I've only been at it for an hour. I can do a bit more. Let's do the Iranian Geo. Yeah, Geo is GeoGebra. It's more, the Geo is more relaxing. I feel more like I will probably get it eventually. With the combo, I'm like deathly scared. Oh, also, I forgot to answer Egnorwala's question earlier. The reason I can pull up the IMO problem instantly is because I have a problem database indexed by problem sources. So I just type IMO 2005-2 into the LaTeX directly and it will compile the problem. So, yeah, black magic. Vim is good. Oh, did I tell you all that I got? I got Mutt working, so now I can type all my emails in Vim from the terminal as well. Yeah. So for me, like I find that if I take the time to write up a problem neatly, which I've been really slacking off on for the last month, then I don't forget it after that. But IMAP labels, yeah, I don't like the Gmail labels. It's okay, because I don't actually use the labels. I basically only use inbox, all mail, and trash. That's basically all I care about. Luke Smith XYZ. I did not use the Mutt Wizard. I didn't find out about the Mutt Wizard until I was like 70% done setting up all the configuration files, and I was like, oh, man. Maybe that would have saved me some time. But it's okay. I like my setup. I learned a lot about IMAP through the process, including the fact that apparently, so my inbox, or my Gmail language is such a traditional Chinese, and I found out that apparently IMAP uses like UTF-7 or something obscene like that. For so the labels just were, how do I deal with it? Yeah, GGB. Alright. Yeah. Or try to run everything in terminals. I actually like it better for the email, to be honest. I'm just like, this feels so nice that I can type my emails in Vim. I think, to be honest, actually, it's not even the Vim that's the main thing. I think the main thing is that now that it's syncing, like when I'm trying to reply to emails, there's no more latency. Like, because when I used to use Gmail web app, like when I load it, it has to first connect to the server and load the inbox, and then like when I'm typing, there's more things. Whereas when I do it with an offline sync now, the sync happens in the background, so that when I decide I want to check my email, there's no delay. It just opens instantly. And same thing, like when I archive the email, it's like instant now. It doesn't, because the changes aren't propagated to the server until the next sync. So that's felt really nice. Like I didn't realize how annoying it was to like have to wait half a second between archiving emails until I didn't have to wait anymore. And I'm like, oh, nice. Yeah. I still use the web app if I'm like composing like a email with like a lot of recipients, because I haven't figured out a good way to send it to like a bunch of recipients at once. How many emails about Otis do you get per day? Like multiple. You don't manually write content multi-part. No, I don't. I have a macro that does that for me. I write the email in Markdown and it gets converted. Yeah. I think there are days where I don't get any Otis emails, and there's days where I get like 10. It usually doesn't go above like 10 a day. Pendoc is great. Is Arch getting used much? I wouldn't know. I think the thing is like Arch has a very steep learning curve, so the only people who are willing to use it are the ones that at least sort of enjoy like playing with Linux systems. And yeah. Yeah, my understanding is actually pretty popular for at least relative to like a lot of other distributions. Okay, alright. I should do Geo. the not yet. So for people in Otis, tomorrow I'm doing a marathon where I'm going to write hints for every red combo problem in Otis. And after that, I imagine you'll get a lot more traffic, because right now it's still basically empty. Yeah, I maybe should not have named it Arch, but it's too late. For people who don't know, last week-ish, I developed a thing called the Automated Repository of Canned Hints, which is basically like me getting tired of answering the same hint requests for the same problems over and over. So I'm starting to just compile them into a database too. I should have done that a long time ago, but I'm getting to it now. Okay, welcome back. So now we have a geometry problem from the Iranian Geometry Olympiad, where I have a circumscribed quadrilateral ABCD, and with a percentage point scale a minute. So immediately, like, I'm not going to draw ABCD first. This is a situation where I actually want to start by drawing the circle. So I equals 0, 0 will be that. And I'll call the in-circle W for lack of a better name. Let's just say radius 1 or whatever. And let's zoom in. Geico, you should project the sides of the triangle onto side BC. Or project the side opposite BC onto side BC. Okay, so there's 4 points on it. K is point omega. L is point omega. Oh wait. Oh, this is an if and only if geo. Oh no. Oh, I can't stand this. All right. So K L M N. Okay, so the lines are going to extend quite a bit, it looks like. Okay, we'll just draw. Okay, TK equals tangent K omega. TL equals tangent L omega. Tn equals tangent M omega. Tn equals tangent N omega. Cool. That's probably the easiest to do it. Those lines look pretty bad, so I'm gonna hide them pretty soon, but okay, and then AD and BC meet at E and AB and oh god, that's off the page. Okay. A, B, C, D, E, F. Is there a way I can make these things like not just all of like every yeah, jeez. It's this one, right? I wanna move that one. Okay, they all fit! Yay! Maybe, not really. Honestly. Oh my god, Geo. That's a problem. Oh jeez. No, 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 no. Oh, you go there. Ha. Isn't AD tension at oh frick. No! Alright, we can deal with it. We can deal with this. Okay, fine. Okay, disaster averted. Okay, there we go. Alright, so KM intersects AB and CAD. Oh my Jesus. At X. We're gonna have to zoom out a lot. CD is not tangent. Wait, what? AB. Wait, okay, what the heck? AD is K. DC is. Oh no. BA. Okay. So I also got the order. Disaster. Okay, so KM, AB, and CD at X and Y. And LN line. Okay, so Kn equals line Km, Ln equals line. Okay, so this diagram sucks. Oh my lord. Everything is off the page. Oh my god. This is a disaster. Were we able to figure it out? We didn't work through the details. So arguably no. This diagram is awful. I can't believe this. Okay, so prove that the circumcircle of xfy is tangent to the circle with diameter ei if and only if Tez is oh jeez. I don't want to do this problem anymore. I can't believe this. Okay, so MK. Alright, let me actually think for the moment. MK intersect AB is like what? So what's the inverse of these? Like I feel like everything here can be kind of inverted. MK. So FXY. So the inverse of F is a certain Mikkel point. I don't remember. No, it's not. F is NN. Okay, the inverse of F is the midpoint of Ln. What's the inverse of X? It's so MK is like that giant circle, and then the circle with diameter IN or something like that. So the inverse of line AB is the circle with diameter IN. And the inverse of line MK is KI. Okay. So how do I intersect circle with diameter IN and the circle with diameter IE should intersect somewhere. Where is that intersection? IN, IL. Yeah. Okay, I'm gonna adjust the points until they're tangent to see if the condition is equivalent to harmonic or something silly like that. Oh my freaking god, they changed it so quickly. Wow, okay. So okay. So what the heck is going on? So the tangency condition is so bad that I really want to invert it. Because this is equivalent to saying like the inverse of xfy is tangent to the red line mk. Problem is I don't know if I have a good description. Well, nothing to do but zoom in. Wow, they were really tangent. Okay. So we're gonna zoom all the way in. And I'm gonna try my best to remember the names of the, okay, I'm not gonna remember them. But x inverse, we'll call it x prime, alright? because I don't know if that's GeoGebra lets me do stars. If ABCD is cyclic. Oh, that's not a bad guess. ABCD is cyclic if only if that's a right angle. Like these things meet at a right angle. So I would totally believe that. Okay, so oh my god. See, now they're so close to each other you can't tell them apart. So now I'm going to zoom all the way in here. And A, B, and C, D. Wait. Okay, F prime is the just midpoint of NL. Oh, that's interesting. It looks like the tangency point is the intersection. Oh, that's very, very interesting. That's good to know. How would you do this construction on paper? I don't think you do. I think you give up and freehand and distort the diagram on an actual contest. Like there's like the problem is like this is with GeoGebra. This is the smallest I was able to get the diagram to be. It looks like this. They're over here. Like there's not enough space. But yeah, I think our guess is right. That feels right to me. That these points are cyclic exactly when it's a right angle, and if it's a right angle, then it's tangent at that point. At the current size of the inverse of XYZ, you need to draw your diagram over this ceiling. Yeah. It's super useful to know that this point is important, though. Okay, so what did I say X prime was? X prime was the intersection of I and N. So like that red line and no. Can I just show the cyclic or something? Or I don't know. I don't know exactly what the condition. Like when I vary it, that circle does weird stuff. But maybe what I can say is I want. I don't know. I don't know what I want. I don't know anymore. Okay, but either way, this point is important. This point was important to begin with, and now it's super important. We'll call it G. Why not? So here's the question: is maybe a circle x prime y prime g is tangent unconditionally? If so, I learned something new today. Yeah, that looks like it's true, right? Looks like x prime y prime g might be tangent unconditionally. Okay, why the heck would that be true? Okay. F prime, D prime. This circle is important. We'll name it. I'm being scammed. Why is that true? Because the inverse of this point is not anything super good. Yeah, I agree. G is intersection of AC cap BD by Brian Kahn. But so we at least have an unconditional statement. Unconditional statements are make me not freak out as much. Should I invert it? Back? I don't want to invert it though. Okay. Okay, so which circles were we drawing? We're drawing the circle with diameter IN and diameter IM, right? That's how we got these points. Or IL. So this is a circle through IL, L. They meet at the midpoint, whatever. I don't know. Does line x prime, y prime go through anywhere? If I invert back, do you get the McCall picture? Do I? Okay, let me invert back. So, okay, zoom out. We're back in the inverted picture. No, I don't need point H. So, okay. Now everything's all over the place, but it's xy. And the inverse of g. What is the inverse of g? Polar of line IG. Polar of G is nice, is it? Oh, does that go through E and F? Is that true? I guess it's like, okay, sure. I agree actually. So I should be thinking about this in terms of K and ML. Yeah. Okay, so what's the claim? I want X, Y, G prime to always be tangent to M, K, G, E. And yeah, that okay, if that's true, I agree it should be something about the McKell thing. So think. What are X and Y? So G prime always lies on EMK because of inversion. Inverse of G is not the tangency point? It is. Or like if they're tangent. So the claim we're trying to prove right now, let me hide this. What is this one? Which circle? This is XFY, right? Hide XFY. We don't care about XFY right now. The thing I'm interested in is XYG prime. And my claim is that these are always tangent at G prime. That's a claim. Why is that true? I have no freaking idea. But let me start typing. Why would those be tangent? Thank you, End Encounter, for the follow. Inverse of km is circle ei, which passes g prime. Yeah, I agree. Like that's definitely a tangency point if ABCD is cyclic. Equivalently, if NL is perpendicular to km. My question is, I don't see why this claim is true. This claim is true unconditionally. We know it from the diagram, but I don't see why. I guess. Okay, actually, one approach might be like, we might know some of the angles. I G prime. So IE is a diameter, right? So maybe what I should be doing is I should be taking IG prime and seeing where it meets this circle again. And... well, actually, I don't know what this point is, so that's not good. Oh, what a monster. What is this? Okay. How am I supposed to show two circles are tangent? Maybe I'd have better luck with x prime and y prime, you think? If I like let x prime, y prime intersect line mk at some point and try to show that the powers do the thing I want them to do, is that a viable approach? I don't know exactly where the... Is this anything good? We are not using any condition. Right now this claim we believe is true unconditionally and we're trying to prove it. X prime, y prime should meet red line. Okay. Yeah, the thing that bugs me at this G prime tangency is I don't know where this... I don't have any information about this point. What the heck is this? There's an APMO problem about two tangent circles that is vaguely reminiscent of this, but I don't know that problem well enough to use it here. It's like APMO 2014-5. It's a Casey problem. But I don't know. Yeah, I don't know if I'm well enough to use it here. G prime mx tangent to BC. Seriously? Let's find out. No. I want to go back to the inverted one. So, like the X prime and Y prime are so weird, but they are better inverted than. Are they? I don't really know. So, hang on. So there's two. Is there two right angles? Like, if I look at E and my hypothesis is that passes through X prime, right? Yeah, G prime, X prime, Y prime. Alright, so I'm gonna shrink this circle so it's a little. Here to see what the heck is going on. We're gonna ignore this stuff all the way. We're gonna ignore all the other garbage. This circle, let's color it slightly differently so you can see it. Yeah, so X prime is like a point such that E and X prime are collinear. Really, X prime is the foot from I to En, I guess is the best way of thinking about it. And we'll distort this one a little as well. So EL. Yeah, so I almost don't think that this circle is helpful either. It's like the feet from. It's a center. Yeah, this circle is actually seems like the main player here. And it's like I have this En, this EL. Yeah, M and X prime, Y prime. I could treat it as shoot. And then finally G is like some random thing. It's like this. And I want to show a tangency. What the heck is going on? Okay, I hit the IL circle, so I should accordingly hide the IN circle. So these two circles are orthogonal, right? What am I doing with this random midpoint? This is like the midpoint of a thing, a midpoint of a different thing. And then there's this like G. Hi, Master. We are getting destroyed by a geo problem. Come join us. So if I treat what do I do with the midpoints? That's the real question. Why are there two midpoints there? I wonder if I should invert with center E. Yeah, we think the condition is equivalent to ABC to be bicentric. I almost want to invert this with respect to E because it will take x prime to here, y prime to here, and that's not right. Something's going on. Let me track. I think I'm looking at this picture upside down, but that's okay. Okay, I have to rotate this. I can't think with this stupid upside down diagram. Okay. We think the condition is equivalent to ABCD bicentric, but we're not able to prove it. For so apparently the following statement is true. I have this purple thing. I don't even care about these two green lines right now. Let's clean them up. I don't really care about G prime either. I don't care about T or A right now. I just want to prove this freaking lemma. I don't. Okay, I do care about that red line. So it's like I have EMK. I have a kite, cyclic kite. I am Kime, right? If this was a T instead of M, it'd be kite. It'd say kite. And yeah, whatever. Purple and green are given. And then apparently what the statement is that if I draw this red line, point, intersection, G, this circle should be tangent. And I have no idea why that's happening. Circumscribed means it has an incircle, but we think it probably has a circumcircle if the condition is true. So I need to show that g x prime y prime is tangent. And I am feeling inversion at E. But I can't quite get it. M x prime I y prime k E. Okay, we're gonna at this point, we're going to how do I find x prime and y prime? They are the second intersections of line EN and EL with the purple circle. So you start with the purple kite, and then you pick N and L on the green circle, and you construct x prime and y prime accordingly. Okay, so here we are. So I have a feeling that these might concur. Yep, I have the right feeling. Why do these concur? I have no idea. That's gotta be a very general statement though. Why do they concur? Why do they concur? Why do they concur? Why do they concur? Freaking no! I just want to select the segment, color it slightly differently. Okay, so that doesn't even involve the circle. That's just I have a cyclic hexagon that is fixed by inversion, so its diagonals are concurrent. I really should know why that's true, but I don't. Why is it true that if you have a cyclic hexagon that's fixed by inversion, then the diagonals are concurrent? The higher. The higher? The higher? The higher? The higher? The higher. Ah, yes. Okay, that's by... Right, okay, that's by Brocard. So that point E on the bottom is N prime intersect LL prime. So the polar of that point will... Okay, yeah, it's just Brocard. It's not... It's sort of... You can do it with 2 applications of Pascal. Cool. So we established that. That's G. Now I need to show G x prime y prime. This circle is tangent to MK. And this is strange as heck. I don't... Like, I just don't know what that, NN prime, LL prime. Maybe. With the midpoints? I had the same feeling that I wanted to construct x prime, y prime intersects MK. I'm running out of letters of the alphabet, unfortunately, but let's call it V. Why not? V equals line x prime, y prime, intersect, KM. Yeah, it definitely, I agree, has a Desargues involutions feel. Fortunately, this is one of the theorems I never really became super comfortable with, but... Alright, so it's red. So how would Desargues involution work? It's... For Desargues we probably want the dual, maybe? I'm not sure. But that's a... Okay, there's a quadrilateral. And that quadrilateral... If I want to use the dual, I need an inscribed conic. or something. Okay, actually, I'll put it this way. What do I do with x prime and y prime? V x prime times v y prime. Oh, actually, there's a radical center somewhere. Hang on. So xmc. Okay, so vx prime times vy prime equals vm times vk. Have you eliminated ABCD? We are still trying to prove this claim. This claim I think this claim is the first key lemma I want to prove. And I am really struggling with it. But ABCD, at least for the purposes of this claim, ABCD is supposed to be gone. And I'll have to resurrect it later. But cool show. What are all these point names? G is just that intersection. There's like 3 things that denote it. Some points were inverted. I'll put it that way. I agree this is probably Geo suck somehow, but I don't see it. Thank you, doll. Pavid for the follow. This might have a... The claim inverted is equivalent to the problem? No. It's just a claim, and we haven't been able to prove it, because this problem's freaking hard. Jeez, what the heck? It has to be some sort of DDIT. I think. But I can't see it. reflection of G over VMGK. Okay, so no, it's not. We want VG squared equals VM times VK. VM times VK. That's not quite a projective condition, right? It's like so. Okay, well, I'm gonna add the points. I was hoping maybe I didn't need to. So I think by generalized butterfly theorem, if the claim is true, then V is the center of an involution, swapping M to K, N1 with L1, and G to itself. In fact, so by the dual of oh no, G is the inverse of no, it's not. What? I'm getting more confused by the moment. Yeah, yeah. VM times VK, that's what I've been staring at. And I believe that VN1... There's a unique... By dual Desargues on... Or, no, just straight... By Desargues evolution theorem on N prime and L prime L, also known as generalized butterfly, there is a point... There's a unique point such that VM times VK equals VN1 times VL1 equals VG squared. So actually it would be enough for me to show that VN1 times VL1 is also equal to that thing. So to that end, are those cyclic? Okay, so it's enough for me to show these guys are cyclic. Wait, actually, I can probably just single choose that, can't I? Can I? Yeah, that will do it. Actually, this is cyclic by the shooting. Okay, we got it. We got it. We got it. So by the shooting lemma, yeah, by the shooting lemma, x prime n1 l1 y prime is cyclic. Now construct this point v here. V has the same power, so vx prime times vy prime is vm times vk, so equals vn1 times vl1. However, by the generalized butterfly theorem, also known as Desargues involution theorem on n prime l, we also have vg squared. There's if v satisfies these two relations, then vg squared is also equal to 2, and that gives us you the desired tangency. Oh, also, and the reason g is there is because of Brocart's theorem. Wow, what the heck? Okay, that happened. Great. So we proved the lemma. Back to the original problem. Man, this problem is crazy. Yeah, we're just getting started. That was the first step. Alright, so now I want to hide all the things and go back to x prime. Actually, you know what? Let's keep this. Let's keep it like so. Maybe I will. I think this diagram actually made sense, unlike the rest of the problem. So I'm gonna just mostly try to keep as much of this as I can. Okay, which lines did I hide? Okay, just undo. Undo. Okay, so we might not need N1, L1 anyway. But so we have the tangency that we are looking for, this circle. Now, the problem is interested in if f prime also lies on the black circle. So if the midpoint of Ln lies on the black circle, my goal is to show that the two red lines, KL and MN, are perpendicular. Like that. So that's where we're at. So I want to show f prime. Okay, so I don't care about C anymore. I don't really care about f. This is the picture I want. This is the one that actually makes like any sense at all. I want to show that if this implies also okay. So here, what do I do? I don't have any idea. So if the midpoints of N prime, NL, and LO prime all lie on this circle here, what does that do for me? Well, it gives me some angles, presumably. Let's see if those angles are any good. How do I chase these angles? Is f prime? Yeah. So the problem is what we believe that the problem is now if f prime, the midpoint of Ln, lies on this special circle, this special whatever it is called, then Km perpendicular to Ln and vice versa. Which seems like it's true. Yeah, okay, it's definitely true. I just don't know how to prove it. That's the only problem. So first of all, let's do the easy. There should be one easy direction. If they are actually perpendicular, why are those points cyclic? Because if there should be a good reason why they're cyclic, right? And that reason is I have no idea. What's the reason? Do I angle chase through like there's like 3 different midpoints. It's like perpendicular, perpendicular, and perpendicular. There's probably some Mikkel stuff happening. Also 7 gazillion cyclic quads. Are there any parallelograms? If you can see one, I'd like to know. I don't see any right now, but I've been known to miss things. I want those 2 circles back. Hi, N. This circle shouldn't be. This should be like Okay, so I have some angles. I can chase angles. Right. Maybe, I hope. Is v prime, n prime, y prime, n prime? Where's v prime? No, v n prime, y n prime. V n prime, y prime, n. It shouldn't be. If that's a parallelogram, then by symmetry, VXLL prime better be one as well, which it's not. I have, okay, I'm gonna construct a point. I'm gonna construct the midpoint of n. Okay, wait. So we have three midpoints, right? The only midpoint that we don't have in this picture right now is the midpoint of L prime, N prime. So we're gonna call that, I'm out of the letters. W equals midpoint L prime, N prime. And that does give us a parallelogram because now we have the four midpoints. It's like F prime, Y prime, W, X prime. I don't know if that did anything like at all. Well, okay. There is some ways to chase things. Like F prime, Y prime is like, okay, Y prime G K is equal to Y prime F G, which because of the parallel lines is equal to like some other angle. So some of the angles look like they should be able to move. G prime is McKell point by NPC. 9-point circle? No. Yeah. Okay. So given these are concurrent, yeah, there's a bunch of angles that we should be able to get out of this. So let me just try chasing some of them. So like Y prime GK. Actually, let's go for the gold. F prime GK. That's the angle I am going to try and chase. And it's allegedly, or let's do it in a way I can actually read it. F prime GM is equal to F prime Y prime G because of the tangency. And F prime Y prime G is, oh jeez, I want to move F prime Y prime to like NL prime or something like that. Maybe that's not gonna work. Maybe I should just use complex numbers. That sounds like a bad idea. Like there's like little, okay, let's try the following angle. So x prime gm is apparently equal to x prime f prime g, would equal to n prime l n. That's a reasonably good angle. N prime l n, I will. It's like n prime k n or something. So I can transfer it all the way to the arc of the green circle. Meanwhile, can you restate it without MNE? Maybe it meant MKE. Yeah, the midpoints really suck. Maybe I should transfer both of them or something. So x prime g y prime. Can I do anything with that? Is W the orthocenter of gx prime y prime? Oh, no way, right? Maybe. Yeah, you're correct. It is indeed an orthocenter because that we already know this actually because oh wait, okay, that's interesting. This is an orthocenter? Really? Because xw prime is perpendicular to f prime y. So it is true a posteriori. Interesting. So this is a parallelogram, I agree. And okay. Okay. Huh. That's interesting. So if f prime g is what's the condition? I don't know what's going on anymore. I agree it says orthocenter g prime x prime y prime though. Posterior. What I really want is some just sort of angle trace to like get the thing I need. Like x prime, f prime, y prime is an angle I can compute because f prime, y prime I can dilate to nl prime, and x prime, f prime is n prime l. So, yeah, that's the difference of these two arcs. Meanwhile, what is angle x prime, g, y prime? I don't freaking know. X prime g, y prime is angle between ln prime and n prime l. Oh, do you have, wait, how do you get that unconditionally? Because that's what I need. Because right now what I have is like if f prime lies on the circle, then x prime g prime y prime is like x prime f y prime, and then I get the two dilations. If there's a second way to get at that angle, I want to know. X prime f prime and f prime y prime. Okay, I think we had the same one, which is okay, fine. I thought maybe we had two different ways to compute the angle. Looks like we have exactly one. What does the short angle condition mean anyways? Like, it bugs me a little because it's like not really symmetric. These two circles are... What does a right angle there mean? Maybe I should go after f prime x prime g. F prime x prime g is... What is the locus of f prime if L is shifted? I mean, it's a circle... Yeah, it's a circle with diameter in. How do I do this? I want to show that ln is going to go perpendicular to mk if and only if that red circle passes through f prime. Maybe I should be looking more into the orthocentered thing. So it's x prime w, f prime y is a parallelogram. That's pretty strong. So I have this circle, and then I had a point that lies on g, w. Yeah, so it's already given to lie on there. So what does that mean actually? If I have a point and its reflection, take the reflection.
Swipe left for stickers.
Echo cancel. What did? I don't know what my echo was doing. What are my thoughts on cat emotes? These fine, sure, but I don't know. They exist. I agree complex is very feasible at this point. Like, all of these points are very computable. I would use n prime, l prime as the free variables. Compute this midpoint, this is a midpoint, this is a midpoint, this is the intersection, and say these four are cyclic if and only if this guy is in the same direction as I, E. So I agree it should be very doable. The cyclic part might be the most annoying part. It's like showing that those points are cyclic or something. But it's there. For sufficiently. Yeah, I don't know what I'm supposed to do with the midpoints. Um, I wonder if I can show like the orange and red lines are always isogonal or something. Is that true? Ah, frick. Huh. Okay, new claim, new claim. Uh, New claim. Orange line and red line are isogonal. Why is that? You think it's spiral? I don't. The triangles don't have the same orientation though. Uh. Oh, okay. Here's the reason. N prime Gn and L G L prime are similar because of the cyclic quad, and then this is half of it. This is half. Yeah, they're corresponding parts of similar triangles. So then you, in particular, you get isogonality. Okay, so if f prime lies on the circle, then w lies on it. Or sorry, f prime lies on the circle. Let me get this straight. If f prime lies on the circle, then if and only if so there's an isogonality lemma or something, right? Like that says even if f prime doesn't lie on the circle, this promises that the extension of y prime w to here and x prime w to here makes a cyclic quad. Like it promises that gx prime w is equal to gy prime w. Those angles are always equal. So I bet there's only like one point such that the reflection. Yeah, yeah. This should be almost basically enough. Okay, so those triangles are all unconditionally similar. Honestly, I wonder if I can just get it from here. So n prime, x prime, y prime. With the isogonality, that should give an orthos and her, right? So f prime is so that's a parallelogram, but also w lies on the isogonal. That should only happen for maybe. I need to double check that. So that angle is equal to that angle. Yep, that uniquely identifies as the antipode. That is sufficient. So if it's on the circle, then it's the antipode. Conversely, if it's the antipode, the same argument should work in reverse, I think. Or if there's a right angle there, then it should be okay. I believe. I think that should work. Yeah, the trick is that those two triangles were actually unconditionally. Yeah, there's unconditional isogonality. So I focused on just the red circle, and on one hand, there's like f prime, like you have this parallelogram and the isogonal always. What that promises is that the angle formed by this x prime f, and that is equal to the angle formed by this and this. So if f prime is on the circle, then you get the right angle. If we have the right angle here, yeah, the orthogonal lemma should do it. First one, yeah. Conversely, if this is a right angle, then what? Actually, the converse direction is a little more confusing. Oh no, this is if it's a, then this is our line's a diameter, so this line is an altitude. So this antipode must be for this altitude. So this is a circumdiameter, and then f prime is. Okay, if I know these are right angles, this is a right angle. Why does f prime? Why does it bisect f prime? Again, I have both a parallelogram and well, okay. Well, I just argue that f prime has the correct angle, right? Because something maybe. And it's part of a parallelogram. Yeah, but I think that isogonality lemma is the trick here. This is quite annoying to write out though. So it's if I have the right angle tangent, da da da. You know, there's the midpoint. I draw the two midpoints. They may not lie on the circle, but they lie on isogonals and are reflected. Yeah, okay. The only point that satisfies that is the zoom center. Okay. That's a weird argument, actually. I don't like... It feels crazy to me, but I think that's correct. So the orthocentered thing turned out to be the thing I needed to use. Okay. Alright, we can call it from here. Wow, what a problem. Can you repeat your argument? Yeah. So once you have this isogonal, this is actually easier if I just draw a separate diagram. So this is what the picture looks like. You have g prime xy. Sorry, I got the primes completely wrong. The argument is I have g, x prime, y prime, and I was able to show that there's two isogonal lines. And f prime and I forgot the other one. W, we call it W. Make a parallelogram here. It's a really bad parallelogram. We'll distort the picture slightly so that it looks better. Still does not look like a parallelogram at all. Alright, that's not much I can do about that. W, so this is f prime. So basically, what we are hoping is that W will be the orthocenter and f prime will be the antipode. Okay, so this picture is completely off actually. Screw it. Bye 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 bye. Around here and around there. Okay, so basically there's like two constraints that are given. There's an isogonality constraint and there is the parallelogram constraint. And there's some possible additional hypotheses. You could have, in one direction, you could add the condition that f prime is on the circle. In the other condition, you can add the constraint that these things are altitude and diameter. And basically, like, because of Geo, if you're given 3 of them, the 4th one follows. So any 3 of these conditions will imply the 4th condition because there's not an just by like counting the degrees of freedom or something. I don't know. So basically, any 3 of them imply the other one. So that gives us the if and only if you want. It's hard to write out. I think I would need to like sit down and think a little bit about it, but the orthogonality lemma is the thing that tells you that these first two conditions unconditionally tell you that this angle is equal to this angle, which is pretty good because you also have like the parallelogram itself. So if f prime is on the circle, it will give you a statement about arcs that will translate to saying that f prime is on the circle. And if you have altitude and diameter, then you should be able to also extract cyclic, I think, just by chasing the angles. G x prime f G y prime G x prime f prime. Oh, good point. Yeah, that's much easier to work with. What am I doing? This is equal to that. Is also follows from the orthogonal lemma applied the other way. Okay, that's better. So if f prime is on the circle, then they're definitely right angles. And conversely, if I have altitude and diameter, yeah, f prime will just go on there. So we're okay. We're just okay. Everything's fine. If I have altitude and diameter, then I can compute all the angles explicitly, and yeah, those angles are too fat. Should I just write it out? If this was actually a right angle, and then this passes through the antipode, then call this alpha, alpha, beta, beta. This is 90 minus alpha minus beta. So this is 90 minus alpha minus beta. And this angle is equal to whatever it is. I feel like I didn't use a condition somewhere. Data. Hang on, how do I get these to add up? Ah, crap. Help. This part's supposed to be easy. I claimed it was easy. No, I can't do it. Okay, oh no, okay. The point is that now I know this angle, because this angle will be 180 2 alpha plus 2 beta plus theta. So this one is as well. Wait, now I'm confused. What am I doing? Who am I? What's my name? Oh god, these angles. Like, the claim really should be that the only... Oh, I see. Okay, the problem is that's actually false if the triangle is scaly, if isosceles. Okay, that's why I can't prove it. So I need like gx prime to not equal gy prime. I see. Okay, the claim is actually false if gx prime is equal to gy prime. But if that's so, then the point v doesn't exist. And yeah, you can try to... Yeah, that's gonna be a very annoying uniqueness argument though. But it does. Yeah. Okay. Okay. I see. As long as G they are not the same line, then there's a good pair that we know that's like this. So there can't be another bad pair like this because that would give us a parallelogram whose opposite sides meet at G, unless gx prime equals gy prime, which is the case only if there's no way I can do it with this k element, right? Because we assume that this would require G to be the midpoint of Mn, which would require k element to be a kite, which would require the tangent L and N to not meet. Okay, so we're okay. Oh, Jesus. Okay, now we're actually done. What a problem. What a day. GG! We did it! What is that? To be honest, the solution is not that long once you compile it. Like I spent a lot of time looking at it, not knowing. The problem is there's too many points, and I couldn't tell which points were important until I saw that important claim. I don't know. What a monster! Oh Jesus. Nope, American. Because the problem is I had to use Desargues. I had to use generalized butterfly, in order to, get it right. Like there's a point where I said, by generalized butterfly theorem. Yeah, this is. No, this is going under American Geo, which I need to rename at some point, because that name is not. I'm a little not sure whether to count this as config geo or not. I'm leaning towards yes, but it could go either way. How does one create this problem? Oh my god, good question. I have no idea. GeoGebra strong. GeoGebra was so overpowered. What a day. I don't know if I have the wind in me to play video games anymore. Is there anything people would like to play that won't? What will the proof look like not inverted? I have no idea. The problem is like the original condition is about two like pretty random circles. Okay, maybe not that random, but I don't know. I thought fx prime y prime was pretty random. And I guess you know what the tangency point is? It's like the inverse of G, but like also like it's two circles tangent, right? Yeah, like the DIT step does not invert well because it's about powers of points on a line, and there's no analog for that on a circle. So it's I don't know. What a problem. Jeez. Oh my god. DIT on a circle. Good luck. Let's try P5 now. Next stream. You can submit Prom 5 next stream. I'm bust. I'm out of it. What's on Steam? Oh, it wants my. I want to rename it to like config geo and classical geo because I think. So for people that don't know, in Otis there is a unit that's called American Geo right now, and it's like a mix of like very classical geo and very config heavy geo. and I want to segregate the two. So one is like about things that are actually very configuration heavy versus classical feeling but not necessarily configuration heavy. And yeah, so that's been on my to-do list forever, and I still haven't gotten to it. The reason it's called American Geo is because I submitted a bunch of such configuration heavy problems when I was in my early undergrad. That was back when the USA just didn't have problems pipelines, so everything was sort of touch and everything's kind of pretty touch and go. Oh, I actually have quite a few Twitch, or not Twitch, I have quite a few games. Stefan Sausage Roll. Parade. Yeah, I don't know. A cool Sokoban demo called Jelly is Sticky. Is that so? Man, I feel like I'm playing. I play so many Sokoban games. Oh wow, that looks very pretty. Also, holy crap. Oh man. So people who cares, this is what it looks like. That's what the trailer looks like. Oh my god. Spring 21. Yeah. Yeah, I think what I really want is like 3 years off to just like go through this list. Just like play all the video games. I'm sorry. The problem so I said this on this random talk I gave on Wednesday where I was like, video game design has one of the worst ratios of time spent developing to like time spent by player, like audience, time spent by audience. It's like one of the worst ratios. And when I was a kid, I treated video games as a way to pass time when I was bored. And now that I'm older, I actually can appreciate like the things that the game developers do, like the little subtle decisions they make, or like the way they theme the game, things like the art, the soundtrack, so on and so forth, that I just like never appreciated as a kid. It's too late now. I don't have enough time. Now I can't just play video games all day. I probably could have in high school if I wanted to. Maybe. Too late now. Puzzle games, yeah. Yeah, I am a big fan of puzzle games. You can probably tell from this collection. Okay. Yeah. I should at least play through The Witness. The problem with The Witness is like it's a 3D game, and 3D games make me dizzy very quickly. Like I tried to play it, and then after like 3 hours, I was like, I don't feel so great. But I've heard a lot of really good things about it, so I should go through it. Hyperbolic Sockabon. Well, see, the Hyperbolic Sockabon was still 2D. So it was like not that bad. Yeah. Maybe what I should do is just like randomly stream on some Saturday nights when I feel like playing video games. And that will force me to like get through these games a bit more. Just block out time to play through these games. Because they are on the whole just really well done. I never appreciated that as a kid. How far did you get into Hollow Knight? Not very far. I've only played Hollow Knight on stream, so I cleared like the first area. I only have like 3.5 hours logged. Yeah. Okay. Mhm. Besides competitions, do you think there are things we should look into as a high schooler for math that are less competitive? I think broadly speaking, you should do things that feel interesting to you, regardless of what the quote unquote right thing to do is. I think people have a tendency to hurt themselves in their own confusion by like trying to deliberately do something because someone else told them that they should do it, which is why I'm typically hesitant to recommend things because people take me too seriously. Yeah, like, you know, even if someone frames the question as like, if I wanted to be a mathematician when I grow up, like, what would be the most beneficial thing to do in high school? I feel reluctant to answer this question because I'm not even convinced that you should know in high school whether you want to be a mathematician. Like, it is very difficult to get serious research experience in high school because math is so inaccessible as a field in general. It's not impossible, but like, a lot of things that are high school research projects are specifically chosen as like high school research projects. Like, there are a lot of constraints on what you can have a high schooler do. It would. Anyways, let me not go too far into that. With those very large disclaimers, yeah, with those disclaimers, very broadly speaking, aside from math competitions, well, I think just learning more math is good. Like, I think when you are in high school, you do not even know enough of the. Like, you should start by learning like what a group ring and field is and what like compact set is. Like, do your due diligence in like basic algebra, real and complex analysis, and then start branching out from there. I used the word should. I promised I wouldn't do that. Well, that's like a good place to start, if you want to do some math that isn't competition math. There are also just like there are just programs out there, basically designed to be like with people like this in mind. Like, there are math circles. I know Simon's been doing his thing with the Euler circle, and so on and so forth. Yeah. But like, my main thing is you should do these things if you are actually interested in them and not just because someone told you that math contests are not real math and you feel bad or something like that. First chapter in napkin before starting linear algebra. I think that is the right approach, honestly. Yeah, it's hard to say. I grew up with groups before. I learned group theory and then ring field theory before learning any linear algebra. In fact, it was separated by, it was separated by 2 or 3 years. Like, I didn't learn any linear algebra until 2 or 3 years after I learned what a group was. There has been some thoughts that it is maybe better to do rings and fields before groups because your rings and fields are commutative and the examples are more natural. Like, modding out in a ring is a lot more natural than modding out by a normal subgroup in a group, I would say. But my understanding is most people still prefer groups first. By which I mean, I forget exactly who gave me this comment, but there was a professor when I asked about this on Facebook. There was a professor who said like, yeah, some of our teachers tried switching to rings fields first, and most of them eventually switched back to groups first, or something to this effect. I don't remember the exact quote or who it was anymore. So yeah, apparently groups first is still more natural because there's fewer operations. Shuck. Will going to a summer camp like Ross help at all with competition math, or is it all research? So I should start by saying I don't actually know that much about the Promise and Ross curriculums, so I'm not really qualified to answer. With that disclaimer, I would say I would be very surprised if it completely didn't help with competition math. Like, it would be very surprising to me if it was like 100% useless. But I don't know. I can't say about like 98%. But it probably won't be 100% useless. Like, if you learn what quadratic reciprocity is, that is probably a good thing. Also, yeah, if you just learn to be like careful and thorough, that is also worth something, right? Like, learning good study habits is a thing that can happen and will help you. It's not all about the specific math. That's true for almost all education things, broadly speaking. Like, there's a thing where it is good as a high school student to learn how to learn something very deeply. And the best way I think to do this is to pick one thing and learn it very well. It doesn't matter if it's like math or if it's computing or even like if it's like StarCraft, ping pong, I don't know. Ping pong was the example Richard Russick gave. Like, if you pick one thing and learn it very well, you will get some lessons out of it that will transfer to a lot of other places. Yeah, StarCraft in particular. I think StarCraft teaches certain lessons about like how to deal with pressure and ego like better than math contests. Like, I think if you play StarCraft competitively, you will be better at not getting tilted than the math contest kids, because the math contest kids only have like one, there's only one USMO per year, so there's only one time when you're really, really under pressure. Whereas StarCraft is like that every game. StarCraft is also there's a rating system, right? So when you lose a game, it is your fault, and also your rating goes down, and you just have to learn to like deal with it and be like, yep, I lost the game. That's a chance for me to get better. Have the right mindset, because if you are one of those, if you don't establish mindset, you will very quickly burn out of StarCraft. It is not at least as a 1v1 game, it's not gentle. It is very ego crushing, and I think like going through that experience was something that taught me a bit about how I should like try to teach math contests as well. Yeah. Also, I think StarCraft really teaches you a lesson to like learn your fundamentals well, because I think when people play StarCraft, there's always this thing where you're like, oh, maybe I'll try to come up with something creative and like, maybe I'll get something out of it, or you try to like make up your own strategy, or be like, oh, if I just learn how to like micro my Marines better, then I'll improve, and then reality shows up and slaps you in the face, and you eventually realize that you realize like, yeah, you just have to actually sit down and like get your fundamentals down, so you're like, I don't know, you're not floating like 1,000 minerals every game or something like that. And you learn that lesson very well. It's like you just can't, you can't just outsmart people that easily. You have to actually spend time learning your fundamentals well. Yeah, exactly. I have this tendency as well, where like the first time I learn a game, I like really try to outsmart it, and it just never works, because when you first start learning something, you don't have instincts. If you don't have instincts, you die. Oh, that's why experience is so important, because experience gives you the right instincts. There's a saying in Go, where in Go there's what some people will tell beginners is you should just lose your first 100 games as quickly as possible. Like, most of the thinking you're doing is probably just bad thinking. Just get some instincts first. Yeah. This is also why, like, whenever people ask me like what book should I read, I always feel a little queasy answering it, because I feel like they're trying to just like, I don't know. I think a lot of it is people are trying to look for some promise that if they do it with a thing a certain way, then they will improve. And I don't make these promises. That's an interesting point, actually. I would believe that, yeah. Yeah. You know, what is the exact book I should read? What is the best way to get 130 on AMC 12? What books did you read? Etc. etc. I get so many of these. And I just always feel like they're asking the wrong question. I feel a little bad being too dismissive because sometimes it is just like I literally have no idea which books are good. Like I have seen all these book titles and I have no idea what any of them mean. Can you tell me which one I should start with? And I'm like, okay, like fine, that's a reasonable question. I can like tell you. But the other people are just looking for like a promise that if they read a certain book they'll get better. And I don't know. I don't really think I can make a guarantee like that. So what percentage of your useful level knowledge would you say came from studying and looking around on your own versus from stuff like mop books, handouts, or instructors? It's a bit of a fuzzy question because it's not clear what it means to learn something from a source. Like, you know, I definitely went to mop and someone told me that like, I don't know, what's a random example? Like, someone might have told me that when... Oh, yeah, someone might have told me the statement of the lifting the exponent lemma or something like that. And, you know, I might have been able to remember the statement and that's about it and not really understood what was happening until later. If you want a number, that number is small. I would say, came from studying and looking around. I would say that the amount of stuff that I picked up in formal instruction is probably on the order of like 20%, maybe. Most of it is really just doing problems on your own. Like, I think I learned... Definitely when I was in MOP, I was of the camp that felt that different people get different things out of MOP, but I was one of the people who got more out of the practice tests, which are literally just like, here are 4 random problems, and work on them for 4 hours. And I feel like I got more out of that than I did from like the actual classes. The feedback on whether this is the case across most people is usually pretty polarized, although I think in most years, most people... So at the end of MOP every year, there's like a survey, right? Where we say, you know, which things did you find helpful, which things didn't you find helpful? And every year up until 2020, classes always came out on top by like, not a huge margin, but like a comfortable margin. And then 2020 was the first year it flipped because online classes are so hard to teach well. But the tests are exactly the same. You send the test as a PDF, and then the student prints out, works on it for 4 hours. But yeah, it's to the point where like sometimes I can point out specific problems that said like the reason I like after I did this problem I realized I now understood X topic. Yeah, for Eknawala, I think that assessment is probably largely true. There is a lot of variance in what classes are helpful for any given person, and yeah. I mean, there are definitely also moments where I can say, like, I learned this lemma from this class. Like, I was sitting in this class and the instructor told me this thing and I was like, holy crap, I didn't know that was true. Yeah, learning about various sequences. We haven't had a fairy sequence class in a while, actually. In part because I don't... Maybe I should teach a fairy sequence class this year. Are there people you have met that can look at any problem and summarize feasible approaches relatively quickly? I... Yeah, I'm assuming you mean Math Olympiad problems. Yes. It also, I mean, it depends on, like, what kind of accuracy you want. Like, if the question is, is there a person who can look at most Olympiad problems and say within, like, 10 minutes tell you, like, basically the method would either be A, B, or C. That's a very high bar. But I think you can... Yeah. I will say there are people who... I'll put it this way. You count the number of problems they don't solve on one hand. Like, I have seen on a few occasions a person who became so strong that when they, like, you basically expect them to get a perfect score on any reasonable Olympiad exam. You get a person like this maybe once every few-ish years. Like, I remember Alex Gunning was said to be like that. It was in the British IMO report. There was a line that was just like, Alex Gunning was so good that no one remembered the last time he didn't solve an Olympiad problem. And MOP 2016, there was one student that was like this. On all the practice tests, there was one problem he didn't solve because it was 2015 A6, and everything else he got. He like lost a total of 10 points at MOP out of like 200 or 300. How many points for the year? It's probably about 200 points. So at the very least, there are people... It is possible to reach a level where, like, you can basically solve most Olympiad problems. But it's... There's, like... Those are rare. There's, like, definitely less than one per year. Yeah. No, yeah, I agree though. Like, there's a sense in which I can... You can craft arbitrarily hard problems. Like, math difficulty is unbounded. Yeah. I mean, they've seen so many problems to develop instinctual feeling or have an in-depth understanding of the grand workings of math. Depends on which person. I think it's always I think the difference is there's some people who are just have done a lot of like Olympiad specific problems, but like I don't know. Like, I think that's a question of like how specific was it to Math Olympiads in particular, and that varies by person. I've seen both. That's fair. Yeah. It turns out that people can just be really good at things. Like that's one thing that you learn from math competitions. It's like, wow, like if you work hard at something, you can get really, really good. Not definitely will get, but like it's on the table. Yeah, like as much as I like don't like this motto that hard work implies success because it implies if you work hard, you are promised to do well. I think the more accurate statement is you are basically always surprised at how far you can get just by working hard. Yeah. Math is weird. It's like, I think it's really ironic that math, which is like the most logical discipline, is still like so personal. Like, despite the fact it is completely logical, it is still like solving math problems is still like extremely personal. That's one of the really beautiful things about math, actually, in my opinion. Because even though a priori you might expect it's just like logical manipulation, like there's a set of rules, and then there's a set of things you can do with those rules, it still ends up feeling like such a human activity. I'll think about this. Yeah, trust is reasonable. I can do almost DSMO P1, P4 problems, but it takes me 2-3 hours. How to improve it? I'm finding it hard to give any useful advice based on just that information. I will say, in general, getting faster is mostly just about, like, getting more experience. Like, I think there's a really big difference between, like, being able to solve there's a point where originally you just can't solve a problem, like, period, given reasonable amounts of time. And eventually you get to a point where you can solve it, like, eventually, given, like, a few hours. And getting from there to solving the problem in, like, less time is mostly just, like, practice more, I think. The scary part is getting from the point where solve at all to solve, like, can't solve at all to, like, can solve in some amount of time. and then you just need to get faster. Yeah, if you want better advice, you should give some examples of problems that you couldn't solve and what you tried on them. Then I'll actually be able to say something concrete. Otherwise, all I can do is like say random vague things. I should just run some one-off game streams. Like, I don't know, if I'm feeling... Just like schedule a few hours every month to play through some of these video games. Preference for Bash is preference to not practicing Geo, please. I beg to differ. Yeah. No, that is true though. I was probably an exception because despite being someone who really enjoyed Geo, I developed an entirely new method to bash Geo problems. And I felt bad. But yeah, there's definitely a camp of people who are like, they just don't like geometry, so they're like, oh wow, there's a way out. Sort of. But that being said, I really do think like so if you take like if I teach a complex numbers class, the thing I will always tell you is that you can't turn off your brain. Like you have to still treat it as a geometry problem. Like when I teach a complex numbers class, on the handout I put a page limit on each problem, where I'm like, your solution should not go over this length. And the reason is that if you have more than that length, then you didn't set up the problem up correctly, and you should fix the setup. Because the way you choose your unit circle, the way you choose your variables, the way you compute your points, like the choice of how you do that setup matters much more than your ability to actually expand. So yeah, page limits. If there's an undiscovered coordinate system. Well, you can join the moving points hype train if that's what you're interested in. Just don't mess up. Moving points is the scariest one because it's hard to tell when you screw up, and if you screw up, you don't get any points. Like with complex bash, it's like if you make a mistake, then the calculation doesn't check out, and then you know that you need to like debug your work. But moving points is not like that. Like if you make a mistake, you just die, and you don't even know it. Yeah, that's the thing about bounding degrees of polynomials. It's so easy to mess up because it's not intuitive at all. The story I tell is that basically at MOP what happened was we gave a moving points lecture because people were really interested in it, and then like people tried to use it on like TSTST, and like of the 10 solutions, like one of them worked. And then they tried it again on like winter TST for a problem that it was actually pretty straightforward to do with moving points. And of the solutions, like half of them worked. So it's so bad, like people just can't get it correct. So I tell them don't use this if you don't know what you're doing. Like, you know. Do graders actually check your complex bash if you do a really long one? The answer is yes. And The answer is called we use Sage. So the first thing I do is I type in the expressions into a computer algebra system and then match them term by term and try to see if there's a mistake. If there's a mistake, you circle the mistake and then you're really happy because you don't have to grade it anymore. Yeah. I think the longer it is, the more likely we are to like try to look for like. Well, no, actually that's sorry. The right phrase is the longer it is, the more of a vengeance we have. Like the more we are hoping that the solution is wrong. Yeah, more vengeance. But yeah, it's so annoying to check. It's not that bad because so the nice thing is that most of the time, if people do a really long complex bash, either they don't finish or they mess up. So it's actually not too bad. Like it's pretty rare that someone does a really long calculation and actually gets it right. Usually there's a mistake. Are you at the level of forefront research, Beth? No, I haven't even passed my qualifying exams yet. I'm not close. I'm not anywhere close. I think people have this misconception that I'm like really good at math. I'm not. I don't think this is really true. I think I'm like pretty good at competitions, but I'm like only average. Outside of that context. You like teaching a lot too, yes. If that wasn't obvious. Yeah. How old is projective geo? Pretty old. I wouldn't know the exact date. You can probably just look it up on Wikipedia or something. Wikipedia says 3rd century. So, there you go. Did you explain n-1 EV? Yes. So that's going to be on the video soon. I finally don't have to explain that anymore. Jeez. I had to explain that so many times during like lectures. Because it's not written down properly anywhere. So, yeah. I always just thought of that as smoothing. I agree. But I think it's like really useful to know that like this is a thing that can happen. Like you can just end up with n-1 equal points. It's like mirror head, sort of like you can probably do without it on paper because like you should have that intuition anyways, but it's so nice to know in advance that it's true. Like mirror head promises you that a certain inequality you could have proven with AMGM is actually true, and it's actually mirror head is actually if and only if, which is a really nice thing. Like if mirror head, if it's a straight symmetric inequality and it's false, and it's not mirror headable, then it's false. Not like a composited one. Like if you have like one symmetric sum against one symmetric sum, the inequality works if and only if it's literally mirror head. So this is like a really nice thing to know, right? Like you don't waste time trying to prove a false statement because you're like, oh, mirror head didn't work, so it's like those particular two sums don't match. Now, obviously, if you have like most of the time, you'll have like more than that, and so like you don't get any promises. But it's really nice to know that at least like if it's a single symmetric sum, it's been worked out exactly when it's true. Three variable cyclic inequalities are not that common. Just inequalities in general are not super common these days. But they aren't dead either. We know that because there was one on IMO 2020. And it was that inequality. I have some mixed feelings about that problem. I'll put it that way. Can the Cartesian plane be generalized into a sphere of infinite radius? Sort of. I think usually what happens is you add one point and then you make it into a sphere. So the inversive plane is basically like this. Like in the inversive plane, you have the plane plus like one point at infinity, and that's actually basically just a sphere. And inequalities, yeah. In general, the fashion trend has been away from very sharp inequalities and from like SOS type thing. Yeah, but that's mostly not the flavor that's popular now. Yeah, cyclic inequalities are still up for grabs. Like 2018 A7 that I proposed was a problem that I think 2018 A7 was a problem that like could have made the IMO. And it didn't because apparently we accidentally submitted it to the wrong portal, so it got leaked or something like that. That's why it didn't get considered. Yeah, that intuition I think is basically correct for why CP1 is actually just a sphere. Okay. Yeah. Yep, that is good intuition. Alrighty. How long have we been doing this chill Q&A for? I find Q&A sessions to be a surprising amount of fun because I can start just saying random garbage and no one can stop me. Alright, I want to get to sleep so that I can wake up tomorrow to do some other work. But thanks for hanging out. Hope you had fun, learned something new. Jeez, that Geo problem though. That's about the limit of what I can do, I think. I think anything harder than that I probably don't get on stream. Alright, thanks everyone for support. Yep. All right. Yeah. Maybe I should when I have a little more time, I should schedule some just game nights where I play through video games instead of doing math. Otherwise, it's too serious. All right. Good night, y'all.